And teacher,
Yeah.
about the previous slide, I don't understand. What you say is that in the example, we need to eliminate the predictors that have 2, 3, and 6.
No, we need to, these are, this example has to do with text mining, okay? Or text classification. For example, when you do things like sentiment analysis. If you have one of the keywords that you're looking for, if one of the keywords is occurs only in very few documents, so each observation is a document, and you have one word that does not occur at all in any document. Okay, and then you have that particular word only occurs in 8 documents. Okay, or in 6, 7, 8 in 8 documents. Okay, then what you do is those it doesn't make sense to consider that keyword, because most of the documents do not have the keyword. So it will not help to do the text mining or text classification. It's like in a categorical predictor, for example, let's suppose that you have a predictor that has a range of salary. You have salaries between 0 and 20,000 pesos a month, and then between 20,000 and 150,000 a month, and so on. It turns out that you do not have any case where you have salaries between 0 and 20, then that category shouldn't exist. It's not going to help you. Okay. Now we'll see a deal with this thing in when we have many data points, many observations. We can do this thing by computing the variance of each of the predictors, and if a predictor has almost 0 variance, that is, if a predictor is almost constant, then that predictor is not going to help me. If I have a customer satisfaction index, and most of the customer satisfaction index are, let's say, most of them are 9, and I have 110, and the rest are just 1% of them are less than 8. Then in that case, the customer satisfaction is not going to help, because most of the customers are classifying or evaluating the service as a 9.
Okay, thank you, teacher.
No, you're welcome. So this is the case of multiple linearity, where we have to check if they have correlation predictors that are very highly correlated, and then eliminate some of those predictors. Because if 2 predictors are highly correlated, that means that they're giving me the same information. So I have, if I have 2 predictors with a correlation of 0.9, 90% correlation, or minus 0.9, could be, it doesn't matter if it's positive or negative. In that case, it's better to eliminate one of the predictors that is highly correlated with the others. And this is a procedure, we'll see the function to do this thing later, because we can do a procedure we normally do is compute the correlation matrix for the continuous predictors. It only applies for the continuous predictors. Then we determine the 2 predictors with the highest correlation. Say predictor A and B are the ones that have the highest correlation. They have correlation of 95% in absolute value, okay? It doesn't matter the sign here. Then we determine the average correlation between A and the other predictors, except B, okay? So between A and the other predictors, and between B and the other predictors. And the one we're going to eliminate is the one that has the largest average correlation. So if A and B are very highly correlated, then I check correlation of A with the other predictors, with C, D, E, and so on. and its correlation with between B and the other predictors. And the one that has the highest average correlation, that's the one I eliminate from the data set, from the predictor set. Okay. Now that doing that by hand is painful, but we'll see a function that we can do the same very fast. Okay. And then we repeat these steps 2 through 4 until no absolute correlation is above the established limit. And we set the established limit. We set it at 80% or 90%. Normally it's more than 80. You consider it's high correlation when it's higher than 80 in most cases. Okay. So that's the other issue. We're going to see how to compute this matrix here. But there's an argument in the function we're going to be using that segments, it groups together variables with very high correlation. So positive correlations are blue, the highest correlations are in blue, dark blue, and the positive correlations, and the highest negative correlations are in dark red. So if you see in this heat map, most of the high correlations are grouped together. So that's very helpful to see which predictors are highly correlated. The other thing is categorical predictors and categorizing predictors. When a predictor is categorical, it's common to decompose it as a set of dummy variables. Again, as I mentioned last time, it is not necessary to do that ourselves, but the algorithms usually do that. If there's a categorical variable, the software will split that variable in multiple variables, multiple dummy variables. But that's what's happening behind that. Now, sometimes it is convenient to divide a categorical variable with many categories in a small number of categorical variables. For example, I have, if you look at one of the INEGI's surveys, the home income or something, home income survey or something like that, it's called that survey that they do. They have for the house, for the type of ownership of the house, they have several categories. So they have a category for if you own the house, another category if you rent the house, another category if you are living there for free, another category if you if the house is in the name of your father or whatever. Okay, so they have two multiple categories, but in fact, what matters is whether you own or do not own, for example. Then you change all those categories for two categories. The same happens with whether they classify that, are you married? Are you divorced? Do you live with somebody? Do you live with multiple partners, and so on? So they have several categories. And if you're married or you live with one partner, we can treat that as the same, for example. Then you remove one category. Okay, that simplifies things. A predictor that has too many categories is not very good. Okay. Sometimes we have to add complex relationships among original predictors. We talked about that. And it may be necessary occasionally to categorize predictors manually. Okay. This, of course, will generate a loss in model performance or precision loss. Okay. But sometimes it is necessary to do that. I'm not sure if we finished with the R script. That we started with this R script last time. just to look at the correlation matrix command. Okay. Here. So this is this presentation AM08A. That's the script AM08A also. And that's in bright space. MA08A, sorry. We started with this script. I'm not sure if we finished reviewing it, because I don't remember if we got to the correlation matrix function, in the high correlations.
I don't think so. I think we did only like half of it.
Yeah.
Didn't
Right.
finish.
Okay, let me make it a little. Can you see that script fine?
Yes, we can see it.
Okay. So I'm gonna run. I believe we got up to transformers, let's see, transforming predictors. We looked at the applying the pre-processing to center and scale and to do the box-Cox transformation. We did all that. And let me start here in removing variables. So run the script up to line 148. Because we'll see some functions that are very useful to detect near zero variance in variables, and also to detect high correlations and eliminate the right variables. See, one of the things, tell me when you're ready, okay? The script.
Espera tantito, prof. Ya estoy cargando.
Ready? Okay. Let me minimize this thing here.
Espera, ¿cuál es el script? El AM.
The script is AM08A.
Ok.
Modelado preprocesamiento. Again, we were using the data that comes with the package, carrier package. Are you all set? How are you? You're set? Okay. So there's this function from caret. This is a function from the caret package. This the name of function is near zero var. What this does is checks all the variables that are continuous, and it determines which variables have near zero variance. That is, which variables have almost all constant values. Okay, that's what it checks. And it returns the number of columns, the column numbers of those variables. If I look at NZ bar, tells me that there is no column that has near zero variance in this data set. So I don't have to eliminate any variable here because none of them have zero variance. Okay. This is just to see what happened here. Look at B1, for example. B1, I'm putting the number 5, and I'm repeating the number 5 100 times. Okay. Then I make the last element a number 6. I make the last element of that vector, that's a variable 1, and I make it equal to 6. And B2, I'm gonna make it as a sequence from 1 to 100. Okay, so I have B1 that has a vector of 5s and then has a 6 at the end. And V2 is the sequence from 1 through 100. No? Now, I'm going to make them a data frame. And if I say near zero var df, it gives me the number 1 because the column 1, which is variable 1, has all 5s and 1 6. That's near zero variance. Whereas the other variable, V2, has the numbers 1, 2, 3, 4, 5, 3 through 100. Okay, so it only tells me that the element that has near zero variance is the first column. Okay. And I can specify other parameters here in the near zero var. I can specify a frequency to do the cut. Okay. In this case, I put a 95 to 5 as a frequency cut. So I have more than 95% of the values that are equal there. So, but that's the principle that works with this function. Okay. Now this one is very useful because that's to eliminate predictors that are highly correlated. And we have many predictors that's very useful. First, we compute the correlation matrix. And I'm going to put here, yes.
¿Mande? No, ahorita con eso.
Couldn't hear. Maybe it was not a question or anything. Okay, so I'm setting a range here, seg core, and I'm putting the correlation matrix of seg train. Remember that segmentation train was transformed where the predictors already transformed by the Cox transformation. Okay, right. Say seg core. Structure is a matrix that has 58 rows and 58 columns, because I have 58 predictors in seg train trans. You look at the head, it's just the values for the correlations. That's what that matrix has. It has 58 columns, 58 rows. And now I do the library core plot to do the plot, and the option to cluster the high correlation variables is this one here. When I say order equal hclust, I'm telling the function to group together, regardless of which order the variables are in the data frame, they have to group together the ones that have the high correlation. Okay. And that's the size of the text, okay, to generate the graph. let me expand this thing. And that's a matrix that you have in the presentation, okay? It grouped the correlators together, the variables together, so that the variables with high correlation are together with variables with high correlation, okay? So that's a good visual aid to see how the correlations are behaving. However, going pair by pair to try to see which ones we eliminate will be very painful. We have too many variables here. But if we use this function, find correlation, I'm going to call it this high core. It's going to give me a vector of the columns, the variables that I need to eliminate. Okay, so it does the procedure that I talked about earlier. It computes the correlation between every variable with the others. Then picks the highest two correlations, the variables that have the highest correlation, sorry, and then checks each one of those against the other variables and eliminates the one that has the lowest average correlation with the other variables. So a high core, if you look at what high core is, high core just gives me the number of the column number of the variables that I have to eliminate. Okay, high core gives me the number of the columns that I have to eliminate. It's just a vector. Okay, it's just a vector that has 34 numbers. So there's 34 variables that I can eliminate from the trading procedure because they are highly correlated. I put this boundary here, 0.75, to eliminate a little bit more. Normally, I would use at least 80%, 85% correlation. And now to eliminate them, all I have to do is, I'm going to say, I'm going to call it sectrain X sin core in correlations without the correlations. And I'm going to take the arrangement, the data frame sectrain trans, which has all the predictors, and I eliminate these columns, minus the columns that are listed in that vector. And now sectrain, the original matrix sectrain X had 1009 rows for 58 columns, 58 variables. And once I eliminate the variables that have very high correlation, I end up with only 24 variables, okay? So I'm reducing the number of predictors, okay? Then this is if you wanted to create the dummy variables. There's a function that helps you also do this thing in R. I'm going to use a different data set here. It's data cars. It comes with R, or comes with I forgot with which package it comes. It's just a data frame that comes with caret, I believe. And cars has this information. Let me go over here. It has the price of the car, mileage, cylinder, doors, whether it's cruise, automatic or not, sound, the type of sound equipment, leather, and then the brand, right? It's a Buick, a Cadillac, a Chevy, a Pontiac, a Saab, Saturn, convertible, coupe, or hatchback, or sedan or wagon. These are indicator variables, right? These are indicator variables. This one, for example, in a Buick has 1 in the case that it's a Buick and has 0 otherwise. And Cadillac, the same thing, has 1s only when there's a Cadillac and 0 otherwise, and so on. Okay. If you look at the structure of cars has these variables, and this is the type of data that you have. Price is numeric, mileage is integer, cylinder is integer, doors integer, and all the dummies are integers because they only take value 0 and 1. Now, I'm going to go to the line 219, and I'm going to take a subset of cars. I'm just going to take the columns That's why these have names here. I'm going to take columns 3 to 5. Okay, but it's going to be 1, 2, 3, 4, 5, and then I'm going to take, I'm going to eliminate those. I'm sorry. I'm going to eliminate the 3, 4, 5, and then 7 to 12. Okay, that's 7, 8, 9, 10, 11, 12. Okay, I'm eliminating those. I'm making a subset with those, eliminating those variables. So the car subset, I only have price, mileage, sound, and whether it is a Saturn, a convertible, a coupe, a hatchback, sedan, or wagon. This is one way to get the subset. Another way to get the subset is using the function select from dplyr. And I can use the pipe operator. And what this thing does is takes the data frame cars and pass it through the function select. And I'm going to select these variables, which are the variables that I already selected, but using the native function, just subtracting the columns. I take the data frame, pipe it through the function select, and what I get is exactly the same result. Okay? I get exactly the same result. Now, what the head, I will not take the head here, but let's look at the type of the variables. All these variables are, the types of these variables, I put it in a vector called type, okay? And if I look at type, I'm sorry, if I look at type, it has just if it's convertible, coupe, hatchback, sedan, or wagon. It has the categories, essentially. That's what it has, okay? Then I'm gonna, I can do the same thing, the car subset, for dollar sign type. Remember, car subset already has these few columns, okay? If I take now the column type, I use the function factor and apply the function, apply car subset at the columns 5 through 9. To the rows, I'm going to apply the function to the rows, and the function is which x equal to 1. So I'm going to separate the Cadillacs are the I only have a 1 in the Cadillac row. Okay, so I'm grouping the variables. I'm grouping the type here. If I look at car subset type, I get all the different types in one single variable. Okay, I get I'm creating a variable that has a categorical variable that has as its values the categories for the different cars. Okay. So in the structure of this thing is just a factor with 5 levels. So the variable type, which is now part of the car subset data frame, has 5 levels, a factor with 5 levels, and the 5 levels are convertibles, sedan, and so on. So from a bunch of dummy variables, I converted all those to one single variable that has all the categories. And then to model the price as a function of mileage and the type of car, we can use the function dummy vars to determine how the predictors are coded. Okay. Suppose I'm putting an example here. Suppose that our first model assumes that the price can be modeled as an additive model of mileage and type, okay? So I can say simple mod, it's I just say dummy bars of as a function of mileage plus type is an additive function of mileage and type. The data is in car subset and levels only equal true. That's just so that it creates the levels and the dummy variables. So I can go back and forth between dummy variables and not. Simple mode now has the structure that tells me that I have two variables. One of them is a factor. Factor variable names will remove, and a less than full rank coding is used. So it codes the values as a less than one coding. So if I have six dummy variables, it will code them as 5, right? And to generate the dummy variables, we just simply use the structure that we created in simple mode. Simple mode is only the structure that says what has to be done. And to generate the dummy variables, I use the predict function. So the predict, as you can see, so it can be used to predict a model, to predict when we did the pre-processing, we used it to predict, to apply the pre-process to a data frame with the prediction. If the columns that have a block source transformation performed will be transformed using the lambda that was determined and so on. So the predict works for many things. Any a model or a structure like this that specifies something to be done to the variables. If I predict, now I have I do the predict simple mode in the head car subset, and what I get is this thing here. It's just the mileage, and now I have the dummy variables. Okay, I went back to the dummy variables. So you can go back and forth from dummy variables and to one variable that's categorical. And I can also model an intervention, an interaction. For example, I may think that price is not only a function of mileage plus type, but also a function of mileage plus type plus the interaction between mileage and type of car. So that would be a way to model that with that interaction. And that's with interaction. It tells me here what is done. It's what's the formula, and factor variable names we remove is the same thing as before. They also use a less than full rank encoding. Okay, so I go back and forth with the predict function and the dummy variables function. Okay. Again, you don't, in general, you will not have to worry about this thing because the models can take the single variable as a categorical variable and work it through as a series of dummy variables. Okay. I saw something in the chat here and okay. Well, let me now then go to start another part of the pre-processing, which is it's a very important part, and that's it's part B of the modeling process. It's AM08B. AM08B, part B of the modeling process. Here we're going to talk about resampling, about overfitting, and model tuning, which are very important things. Most of the models that we're going to study here, except for a few ones like linear discriminant analysis or logistic regression, they do not have something that we call hyperparameters. That is, parameters that need to be cannot be obtained directly from the data. Okay, so the concept of resampling is very important to determine to model predictive models, to create predictive models. This is what I was saying, most of the models will be studying here are very, very flexible, okay? And since they are very flexible, they are subject to overfitting. I can overfit a model. So we need to have a methodological approach to evaluate the models and to avoid overfitting. Because overfitting will deteriorate the predictive capabilities of a model when I overfit. And overfitting, what it will do is I will do a perfect, I can do almost a perfect prediction of the data set that I used to train the model, but when new data comes in, it's not a good model to predict. And that's what I just said. Overfitting plays against predictive quality, okay? Because again, if you learn all the characteristics of a training set, then that model can be, if it's very flexible, it can predict almost with 100% precision the data that you used to model, to create the model. Now we use here a simple example of binary classification with simulated data. We have n equals 208 observations. Of those 208 observations, 111 correspond to class 1 and 97 to class 2. So it's almost balanced. It's not very highly unbalanced. And that we will also generate the data so that there is a significant overlap between the two classes, between class 1 and class 2. In this case, you have two variables. The classification rules can be represented as a boundary, as a boundary around the data. So these are the data from class 1 and class 2. Class 1 is the red one or pink one, whatever, between red and pink, and class 2 is the blue. Okay, so they're mixed here. And we need to classify class 1 and class 2. This example here is with support vector machine, an algorithm that we're going to study after this session. And we have a very flexible, this algorithm, the support vector machine algorithm, is very, very flexible. And it has, we'll see it later, it has one parameter, that's the cost of misclassification. That's a hyperparameter. You cannot determine the cost of misclassification just from the data itself, but you need to do something else. Okay. And now, if you look at the picture on the right, this is very noisy. This classification boundaries are very noisy. That happens if I have a very high cost of misclassification. Since I'm using I'm working on the training set, if I use a very high cost of misclassification, it will try to accommodate the boundaries so that it minimizes that cost, that misclassification rate. So this one is very flexible, but it's about predictor, because if I get an observation that falls around here, which is very likely a red one, a class 1 observation, it will classify it as class 2, because it falls within the boundary of the class 2. And this is a case where the classification boundary was obtained by something that we'll study later, that's generalized cross-validation. So the cost of misclassification was not fixed arbitrarily very high, but it was chosen by a method that we call cross-validation. These parameters that cannot be determined from the data, we call them hyperparameters. And the models we'll be studying have hyperparameters. For example, a k-nearest neighbor has hyperparameters, which is k, the number of nearest neighbors. And we need a way to be able to select the right value of these hyperparameters so that there's a right balance between bias and variance of the models. Okay. The model used to classify the sample. In the example is an support vector machine, is what I told you, and using the hyperparameter of the cost, we had on the extreme left we had the very high cost of misclassification, and on the right we had the cost of classification chosen by cross-validation. So as you can see, the model with a very high cost of misclassification is very noisy. It's very adaptable to the training set, but it's not a very good predictor for new observations. Now, there are many approaches to determine the best hyperparameters. And again, we'll focus more on one procedure that we'll call cross-validation, but there are other methods to choose the hyperparameters. The process that we'll be using is we define first, for each model that we're going to train, we define which are the possible values of the hyperparameters. For example, in the k-nearest neighbor, well, I'm going to use 3, 5, 7, 10, for example. I determine which are the possible values of hyperparameter that I'm going to use. Then for every possible combination, some models will have 2 hyperparameters or 3 hyperparameters. So for example, if I have 2, I construct a grid. Suppose that one is in the support vector machine, one will be the cost, another will be a scaling factor or learning rate. Then I make a grid of possible values, combination of values of those 2. And we construct that every combination of hyperparameter values. And what we do is then with the training data, this is all done with the training data, not with the test data or validation data. We resample the training data, train the model, okay, predict using the test data from the resampling, okay, from the resampling scheme. It's not clear in this picture, but we're using the test data from the resampling scheme. We assess the resampling results and determine the final values for the hyperparameters. So that will be the general procedure. Once we have the final values for the hyperparameters, we use the final values to retrain the model, but now the full model with the complete data set. Okay. With examples, the process will be clear. Again, the first step is always pre-processing, then selecting the possible values for the hyperparameters. Then once we have selected the possible values for the hyperparameters, we train the models. So for every combination of hyperparameters, we'll train the model of these ones. We'll see that we'll train them more. But in every time we train them, we train a model with a set of hyperparameters and we have a result, which could be misclassification rate or could be area under the curve and so on. And we evaluate that with the training, with the test data that comes out of the resampling scheme. In the resampling, in general, the concept is I use the training data set. Part of the training set, I use it for training the model, and I test it in the other part of the training data set. And then I change the training data set again within the same data, resample, and and test the data, test the model in the part that I don't use to train the model. So it'll give me a bunch of indicators for each of the possible combinations of the hyperparameters of which are the right, and based on that, we'll be able to determine which is the best model, the best set of hyperparameters for the model. Then we always partition the data, unless we have a small data set. That will be a restriction. But when the sample size is large, we can split the complete data set in two: a set of data that will be used to train the model and a set to test it. Okay, that's what we're using so far. With the create data partition, that's what we're doing. Okay. Now, when n is small, if we leave 20 or 30% out for testing, that may be bad for the creation of model, for the training of the model. Because we know that in general, the more data we have, the better model we can get. So if the data is small, we may have to leave a smaller percentage of data for the test data set. We can do a split that's randomized and non-randomized. In many situations, the non-randomized method to separate data may be appropriate. There's a couple of examples here. If you want to predict the results in patients, and you use the model you train the model with a set of patients with some characteristics, clinical characteristics, but you want to test it in a different group of patients with other clinical characteristics to see how that treatment can be generalized to other patients. That's one case where you don't do a randomized thing. You select, for example, patients with certain ethnic characteristics, and you want to make sure that the treatment you develop is also good for other ethnic characteristics. So, you select a group based on the ethnic characteristics, and then you leave out some people that are not in that group to test them all. In chemistry, also in drug discovery, normally what they do in chemistry, they try to explore a new space, a new chemical space that is not known. Okay, so the main objective is to try to create a model for what you know, what the model space that you know, and then test it in other space. That's done a lot in medical research. To be able to extend the model. Okay. Another way is simple random sampling. Okay, I can make my whole data set, and I can just take a sample at random, simple random sampling, and take 80% for training and 20% for testing, or 70% for training and 30% for testing. Or we can do stratified random sampling. Create data partition, it does stratified random sampling. If the classes are unbalanced, then we need to do stratified random sampling to make sure that in the training data set, we have the same proportions for the different classes that we have in the test data set. Okay. So there are several resampling methods. They essentially consist on resampling from the same data set. Okay. And we do that to obtain information about the model performance, information that we cannot get out of one single sample. We do the resampling to be able to do that. Okay. Now, resampling can be computationally expensive, but now it's not so much an issue nowadays. Okay, it used to be a big issue when we had very limited computing power. Now it's not a big issue. Of course, it depends on the number of data points we have and the number of variables or predictors that we have, how expensive that processing is. We're going to focus here in two methods. One is bootstrapping, and the other one is cross-validation. Have you heard the term bootstrapping before? In density estimation or anything like that, no? Okay. We'll look at those two concepts. The one we'll be using the most here, because it's very robust, is the method of cross-validation. Okay. And we use cross-validation or bootstrapping for two main purposes. One is model evaluation, to try to evaluate one model against the other, for example, to compare models in model selection or to evaluate a final model. So, for example, the first stage would be I select a model, I use cross-validation or bootstrapping to select the model. And then once I selected the model, I do the fine-tuning with cross-validation also. Okay. Fine-tuning, what do we mean by fine-tuning? When we're selecting a model, we normally try a grid of hyperparameters that's not too large, okay? Not very large grid of hyperparameters, because that represents a lot of model estimations. But once we determine which is the best model, then we can do a finer search in that for the hyperparameters that best represent the data. This an example in K-nearest neighbor, we can use cross-validation to determine the value of K. So we'll start talking about cross-validation. How are we doing? Do you need a break? Yeah.
Yes.
Okay. So let's take a break here. It's almost 11:30. Let's go back. Let's come back at 11:45 or 11:40. 11:40. Okay. We'll see you in a few minutes. Stop share.
Thank you, teacher.
Oh, thank you. Thing. Okay. Okay, first start with the concept of cross-validation. I'm going to use a regression example here to illustrate cross-validation in the different forms of cross-validation we're going to see. Suppose we're doing a regression and want to estimate the error rate by adjusting a certain method for a set of observations. Okay. Then cross-validation, what it does is essentially what we've been doing. We divide the sample into a training sample and to a test sample or validation sample. We train the model with the training data. That's simple cross-validation. Okay, we train the model with the training data and use it to predict the responses on the testing data set. So because in the testing data set, I already know the response, so I can predict it and check what's the error in that prediction. Now the process is repeated with new random splits on the data set. So the simple correlation, you do it once, but now if I do it again, I select a random seed, a different random seed, select a different sample and test it. Okay, so I can do that many times. Now we're going to see now these repetitions, the 10 repetitions of this process to estimate the mean square error of a regression model. So 10 repetitions of the same process. What we did here is feed polynomial models of different orders. So order 1, order 2, order 3, and so on. And fitted the models 10 times with different random seeds, separating the set into a training set and a validation set. And for each of these 10 times that we fitted the model, the mean square error was computed. Okay? So for a polynomial degree 1, the model is trained with the data set, tested on the testing data set, on the validation data set, and computed the mean square error. For that was done 10 times. For a polynomial degree 2, the same thing. Okay. So for each grade, for each degree of the polynomial, we fitted the models 10 times. And this is the mean square error of these were generated data. So we know what the mean square error is, in truth, the 2 mean square error. And this is the result of the 10 times that we fitted that polynomials of degree 1. Those are the results. So that for example, this time the mean square error was around 21 point something, 21.6 for polynomial degree 1. Whereas in this case, we got a mean square error of 28 point something. Oh, so a lot worse than this one. With it is a polynomial degree 1, but these are 2 different sets of data, 10 different sets of data that we use. So as you can see, there's a lot of variability in the results when we train the data in a set and test it in a different set. We did that for polynomial degree 1, polynomial degree 2, polynomial degree 3, degree 4, and so on, up to degree 10 polynomial. Now, you can see there's a lot of variability here. Okay, there's a lot of variability in the mean square error every time I use a different set of training, a different training set. Because when I change the seed, I'm changing the set. Now, there is no consensus then about among the 10 curves that we are using here to represent the mean square error. No consensus into which is the best model, but there seems to be some of consensus here in that the polynomial degree 1 is the worst, okay? Because the mean square error is the largest in all these cases, whereas they seem to be giving better results with polynomials of degree 2. Second degree polynomials seem to be better results. There are some cases, for example, this case, a polynomial degree 7 get very good results, but in this sample here, it's really bad results for a polynomial degree 7. Okay, so in all these cases, there seems to be a minimum around polynomial degree 2, but there's no consensus. There's a lot of variability there. So the only thing that comes clear here is that the model of order 1 is not good, wouldn't be good. And the model 2 would seem to be the alternative. Because for degrees greater than 2, we have some cases with good performance, but some cases with very, very poor performance. Now, the disadvantage of this approach is the first one that we just saw. There may be large variations among the results, the rates, depending on the number of observations that were included in the training set and on the observations themselves. So every time we have a different training set, we get a different model, and a different model will give us a different MSE. Now, the other disadvantage is only a subset of the observations, which are the ones on the training set I used to train the model. Since the statistical models tend to have worse performance when we have fewer data points, then that's a disadvantage because we're splitting in maybe a 40-60 split or something like that, which was generally done in cross-validation, in simple cross-validation. Okay. Then that takes us to what's called leave one out cross validation. Leave one out cross validation. What we do here is, again, we split the data set. But if we have n data points, we train with n minus 1 data points and test it in the data point that was left outside. Okay, so it's the same thing. We split in two, but this time the split is not random. I'm going to take the first n minus 1, predict the nth observation. Then I take the first n minus 2 and the nth observation and predict the n minus 2 observation. Okay. We repeat this process n times. So we have many data points. If we have 1,000 observations, we will be doing this process 1,000 times. And we compute the cross-validation error as the average of the errors in each of the n times that we computed that thing. So the first time we get an error and we predicted the nth observation. The second time we get an error when we predicted the n minus 1 observation, and so on. And the average of those errors, we take that as the cross-validation error. That's the error estimated by cross-validation, leaving out 1.
Teacher, can I see if I understood correctly? So you leave the nth observation, and then you leave out the n minus 1 observation, and then the n minus 2, and you keep doing this, and then you see, like, what are you trying to get? The
error, the prediction error.
Is it the mean square error or no?
Yeah, the mean square error is the class what we're going to get.
And then
you do the error squared, the square of the error, and then we average all those.
Okay, and then you average the mean square error of every prediction you try to make.
Right. Now, every time I'm only predicting 1 observation, so I only get 1 error, I square it. And then the cross-validation error with n observations is the average of the mean square errors, which is the square of the error in this case, because it's only 1. Okay, and this picture illustrates that thing. So I take here observations 2 through n to train the model and calculate the prediction error in 1. Then I take 1, 3, and the rest and predict number 2 and get the prediction error for 2. And 1, 2, 4, and on, get the prediction error for 3, and so on. And then I average all those errors, and that's a cross-validation error, leaving out 1 cross-validation error. Okay.
Okay.
That's a LOOCV, leave 1 out cross-validation. This is more expensive. This is a very expensive process because if I have 1 million transactions, I will be doing 1 million fits of the model. Okay. Now, although it can be computationally very expensive, we need to fit the model many times. I mean, as many times as number of observations we have. As you can see here, here's the leave out 1 cross-validation. This is the curve. The mean square error almost coincides. I mean, it's essentially the same mean square error. It's essentially the same mean square error because we're using essentially the same set of data. See, here I'm using this the section in blue to train the model. In the second model, the only thing that changes is that I take this observation 1 and then I remove this observation 2. So I'm essentially using the same set of data. Essentially, it's the same set of data, and that therefore the mean square error, the estimated mean square error, almost coincides. So it's almost coincides for all the times that we did this thing. This is with the leave out 1 cross validation. Now, there's a disadvantage of that. The disadvantage is that the estimates of this mean square error are going to be, they're going to be highly correlated. Okay, the models are going to be highly correlated, so I will have a larger variance. Okay, the variance of this thing will be larger. But if you look at now, the next thing we'll talk about is the tenfold cross-validation. We'll explain now that that's, you can see the tenfold cross-validation. There is pretty good coincidence here between the different curves that represent the mean square error for the different degrees of the polynomial. And it's not like constant with this thing here. But again, this has the disadvantage that since my models are highly correlated, the mean square errors will have larger variance. Okay. And tenfold cross-validation, which is the graph here, is what we'll be using in general to select models and to fine-tune models. Tenfold cross-validation in general, k-fold cross-validation, how does it work? We divide the training set in k groups. We always split first a test set or validation set. We try to be that to be a small proportion of the data, okay? And maybe 70%, 80% of the data for training. With 80% of the data that we use for training, we split it in k groups, only the training group, the training set. The k groups are approximately the same. So if I divide it in 10 groups, that'll be tenfold cross-validation. I divide the training set in 10 groups. Then I use the first fold. See, each one of these 10 groups is going to be a fold. Okay, it's a tenfold cross-validation, so each group is a fold. And the first fold is used as a validation for the model that's trained with the remaining 9 folds. The second fold is going to be used as a test set for the to validate the model that that's trained with the models with fold number 1 and fold number 3 through 10 and so on. This is an illustration of how this thing works. This is my training data, and if I split that in, this is an example with four-fold cross-validation. See, we have 4 folds. The first time we train the model with folds number 1, fold number 2, 3, and 4, which are these three folds here, and we test it or we predict on these observations. The second time, we train the model with the folds that were not used earlier, the first 1, 3, and 4, and test it or do the prediction on the fold that was left out. Okay. And the same thing for fold number 3 and fold number 4 in the case of fold cross-validation. So now, what we are going to be doing is we're going to be doing this thing. And before I move out of this picture, let me put the formula here. We are going to get, for this set that we're predicting on, we get an estimate of the mean square error. Then for this one, we also get an estimate of the mean square error. And for this one, we get an estimate of the mean square error, and for this one too. So I have one estimate of mean square error for each one of the folds. And I average those estimates to get the cross-validation, the k-fold cross-validation error, mean square error. That's the estimate of mean square error. Now, this has advantages over the previous one. One of the advantages is, of course, less computationally expensive, because I'm not doing this, if I have 1,000,000 records, I'm not doing it 1,000,000 times. And I have, if I have tenfold cross-validation, I would only do it 10,000 times, let's say. No? But the other advantage is that although there is some commonality between the data that they use to train Model 1 and Model 2 and Model 3 and Model 4, there's some common observations. they are not exactly the same as in simple cross-validation, which I'm used in the leaving out one cross-validation. All the observations except one is different, are the same, sorry, from fault to fault, from model to model. So since we don't have that much coincidence between the training sets, I have less variance in my estimate of the prediction error. So it has another advantage. Now, what we do is we also, to try to reduce the problem of using the same sample for each of the faults, what we normally do is we split this thing. What we normally do is take the same set, but do a different partition. I'm going to go back to have more space here. I would take the same set and do a repetition of this thing. So I take the same set. But now I take these, and let me split it into 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 8. No? Now, the next time I change the random seed, if this is not going to be my split next time, when I take the random, when I change the random seed, I will have something like this probably. This is group number 1, and the other another piece of the group number 1 is here, and then another piece of group number 1 is here, and then group number 2, and then number 2 I have another piece here, and so on. So if I repeat this process, changing the random seed, I will get a different set of faults. And we'll have, so what we normally are going to be doing is we're doing k-fold cross-validation, but repeated at least 3 times. Okay. So combinations that are advisable to do is I use either k equal 5 or 10. Those are the common splits that we do, 5 and 10. And the number of times that we repeat the process, at least 3. See, if I have, if I use k equals 5, I have 5 folds and 3 repetitions. So I will have 15 estimates of the mean square error. Okay, for a given set of hyperparameters, and then do the same thing for another set of hyperparameters and so on. Ideally, we would do at least 10 times 3. Because remember that the large sample theory, that if we have a large number, we can use the normal distribution for almost everything, right? Well, that's an advantage of using at least 10 folds and 30 repetitions. However, it's not always possible because of the computational time. It's not, and doing the k equals 5 folds. So if you have to sacrifice something, it's better to do fewer folds and more repetitions, because I'm changing the seed, than doing more folds and less repetitions. Okay, that is better. Now you may be limited by memory. Remember, R runs in memory. So if I have a set with 10 million transactions and each transaction has 80 different variables, I'm going to need at least a 32 gigabyte RAM in RAM, and I may not be able to do 5 folds. I may have to do 10 folds, or I may not be able to do 10 folds. I may have to do only 5 folds, so that I have less observations in the data that I use for training. Okay, because in one case with 5 folds, I'm using, with 5 folds, I'm using 80% of the data with to do the training. And if I have 10 folds, I'm going to be using 10% of the data, 90% of the data to do the training. Okay. But these are normally the combinations we try to use. Is the concept of k-fold cross-validation clear? Yeah. Okay. Now, this we're going to see again simulated data, and we're going to see the true mean square error. Because it's simulated, we know what the true mean square error is because we know what the true model is. And its estimate with one-fold cross-validation, which is one-fold cross-validation is leave out one, right? Essentially, no, it's a no, that will be n-fold cross-validation. There's a mistake here. N-fold cross-validation will be the same thing as leave out one cross-validation. Let me correct that thing because that's n-fold cross-validation. N-fold cross-validation is the same thing as leave out one because I'm building n folds, which corresponds one, each fold corresponds to one observation. Okay. So the true mean square error is the blue line. Okay, so the true mean square error is this line here. The n-fold cross-validation or leave one out cross-validation, which is the same, is the dashed line. And the 10-fold cross-validation is the orange line. Okay, that's the orange line. The 10-fold cross-validation. Now, if you look at the three charts, this is with which model was that? I'm not sure if it was a support vector machine or I forgot which one it was, or on neural network, something like that. Anyway, this is the hyperparameter here, flexibility, and that's that could be the case of flexibility is represented by the hyperparameters because that's what gives you the flexibility in the models. So if it's support vector machine, flexibility can be cost and rate of decay of the learning rate. If it's neural networks, it will be the number of hidden units and the number of layers of the neural network, for example. So this is as flexibility increases, you see, for example, the minimum for the true mean square error is around 6, right? And both the leave one out cross-validation and the n-fold cross-validation, the 10-fold cross-validation give very similar results. The same thing happens here. They're both close to the true minimum value, and the same thing happens here.
Teacher, I'm not sure if I'm following what is flexibility.
What is what?
The flexibility.
Flexibility, think of a parameter, for example, think of cost in a support vector machine, or think of K is a K nearest neighbor.
Okay.
See? So if K is very small, I have a lot of flexibility in the model. Remember, we get boundaries that are very noisy.
Okay, yeah.
And
bigger groups.
As K grows, the boundary becomes smoother, but it's less flexible. It's how adaptable the model is to the training data set.
Okay.
Okay. And it will change for each model. For K nearest neighbor is the number of K, the number of nearest neighbors that we're going to consider. For support vector machine is going to be the cost of the misclassification. For example, a polynomial curve, it will be the degree of the polynomial. The higher the degree, the more flexible the polynomial is, and I can make it go through every point in my data set. So the larger the degree of the polynomial, the more flexible. The smaller the degree of the polynomial, the less flexible. Because I just get a straight line. Is that clear?
Yes, teacher.
Yeah, okay, good. So the important thing here is that there, in all these cases, the values obtained by cross-validation and leave-out one cross-validation are very similar to the true mean square error. So they provide good estimates of mean square error. The disadvantage of the leave one out cross-validation is the price variance, and also the fact that it's computationally very expensive. Okay. Now, in general, we're estimating the value of the flexibility of parameter, whichever that is, that gives us the smallest mean square error. That's in general what we're going to be looking for. Okay. And that's normally the case. We're more interested in the location of the minimum, right? And a secondary objective is to understand what can I expect when I use that model in production for prediction. What type of error can I expect? Now let's talk a little bit about the trade-off between bias and variance. Now, if we take k-fold cross-validation with k less than n, because k less equal to n, that's equal to leave-out cross-validation. We already mentioned that it has computational advantages over leave-one-out cross-validation, because you don't have to feed the model so many times. Now, k-fold cross-validation usually generates more precise estimates of the error than the leave-one-out cross-validation. Why? Because of the high correlation between the models in leave-one-out cross-validation, because we're using essentially the same data to estimate the model several times. Essentially the same data. Leave-one-out cross-validation generates estimates approximately unbiased for the error rate, but since each training set has n-1 observation. So it's essentially, it's almost unbiased, but has higher variance. Because what we said, that the set of data that I'm using for training is essentially the same in leave-one-out correlation. So I have smaller variance, but I have a higher bias. The smaller bias, but higher variance. While k-fold cross-validation, well, for example, for k equals 5 or 10, which are common values for k to use, leads an intermediate bias between leave-out cross-validation and cross-validation. And so from a perspective of bias reduction, leave-one-out cross-validation is preferable from the perspective of bias reduction. Okay? But k-fold cross-validation is preferable for than cross-validation, the simple cross-validation. Okay, just splitting the set once. But normally we want to trade off between bias and variance. That's why we usually go with k-fold cross-validation. And as long as we are between k5 and 10, we're gonna sort of in a middle ground between reducing bias and reducing variance. Okay, so we're getting a balance between bias and variance if we use k-fold cross-validation. And this is what we discussed earlier, leave-out one cross-validation, that we're averaging the results of n models trained with essentially the same set of data, so it has higher variance because the results are highly correlated. And k-fold cross-validation, we're averaging the results of k-trained models, which are less correlated. If we do the repetition, if we do repetitions, at least 3 repetitions, then that variance is still further reduced. So that's why it's convenient always to do repetitions. Now in classification, nothing changes. The only thing that changes is that instead of the mean square error, we could use the error rate, okay, which is the misclassification rate, or we could use, for example, the area under the curve, and the ROC curve, if data is not balanced. This is again a set of data simulated from regression models using polynomials of order 1, 2, 3, and 4. Okay. For example, a second degree polynomial involves the first variable, second variable, first one squared, the second squared. It's an additive model. There's no interaction in this model, in the second degree model. Okay, that's a logistic example. And in this case, in the case of classification, again, we use either this thing, the error rate, which will be the average of the errors in each that we obtain with each model that we fit, or would be the area under the ROC curve, which would be the average of the areas of under the ROC curve for each one of the models that we fit. So this is the polynomial that was used to generate the data. And let's see if I have the charts here. Here's the definition of the error rate. Here we're considering error rate. So yi denotes the actual class for the ith observation, and yi hat represents a prediction for the class or category in the ith observation. Okay, so the error rate will be the average of these indicator functions, which is equal to 1 when the prediction is equal to the value, the true value. Bayes classifier, we have mentioned Bayes classifier before, and it can be shown that the error rate is minimized by Bayes classifier. Bayes classifier is the one that assigns the observation to the class that has the highest probability. We have talked about this before. That is, we assign the observation, test observation X null to a class J for which this happens, for which the probability that Y belongs to Y is actually equal to little y, which is the class, given that X equals X null is the largest. So if we have 3 classes and the largest probability goes to class 4, class 3, you will assign the observation to class 3 and so on. That's Bayes classifier. In the case of 2 classes, Bayes classifier predicts class 1 if the conditional probability that the observation belongs, that the response is 1, it's a success, given that the values of the predictors are given by X null, which X null is a vector, right? With the P predictors that we have is greater than 0.5. This is the case with 2 variables, with 2 predictors, X1 and X2. And we have mentioned that Bayes classifier is the one that minimizes the misclassification rate. Okay. This shows the graph that has 2 different classes generated from that logistic regression model that we saw. And the dashed line is the Bayes boundary, the Bayes decision boundary. So that's the optimal decision boundary. We never know it because we don't know what the probability of y given equals to 1 given x equals 0 is. And then the way the curve is produced is we take every possible combination of x1 and x2 and calculate that probability, and the places where it's greater than 0.5, we put it as a yellow, let's say, and the places where it's less than or equal to 0.5 as blues. And the boundary that divides those 2 points will be the Bayes boundary. So that's the optimal boundary. Now, the base error rate is the lowest, and we call it the base error rate, BER. And the error rate when x equals to 0 is the 1 minus the maximum of the probabilities that y equals j, where j is the class 1, class 2, class 3, so given that x equals to x0. In general, the base error rate is the expected value, is 1 minus the expected value of this thing here. Because that's that we only can compute that expected value if we know the probability, the conditional probability that we have there. What the expectation is doing is averaging the probabilities over all possible values of vector x, which has two components, x1 and x2. Okay. In this case, since it's simulated data, we know what that expected value is. And we know that for this, in this simulated data, the error rate, base error rate is 0.13. That's in this simulated data. Base error rate is what we also call irreducible error, because that's since this is computed under the assumption that we know what the real model is, that's the best we can do, and that's the irreducible error. That's the error that we're going to have even if we know exactly what's the function that separates the two classes. Again, the ideal would be to know base classifier, and but we don't know the true probability, so we have to estimate that true probability, and that's what classification models do. They try to estimate that probability. See here, these examples, you have the purple dashed line is base decision boundary. Okay, that's the same we had earlier. Base decision boundary. The black solid line represents the decision boundaries calculated with logistic regression of degrees 1, 2, 3, and 4. Okay. So this is logistic regression with a polynomial degree 1. This logistic regression with a polynomial degree 2, degree 3, and degree 4. Okay. So it looks here like the best choice would be 3, right? Looks like that could be the best choice. And if you look at the error rates, we compute the error rates for the polynomial degree 1 in the logistic regression model, degree 2, 3, 3, and so on. And the error rates are 0.201, 0.197, 0.160, and 0.162. So the base error rate is 0.133, and so therefore the best choice would be 0.160, which is degree 3. Okay. Now here we can select very easily the degree because we know what the base error rate is. Since we do not know it, that's why we use cross validation to estimate that the error rate, because there's variability in the error rate. This is what happens with the error rate. Here's the order of the polynomial used. It's the same simulated data, okay? Generated from a logistic regression model. The yellow line represents the test data. So that's the error rate using the test data to evaluate the model. The blue line represents the error rate using the training data to evaluate the model. And KFCC with K equal 10 represents tenfold cross-validation estimation of the error rate. As you can see, testing the model with the training data always gives very low error rates. And it will always tend to 0. The error rate using the trained data, the more flexibility I have in the polynomial for this logistic regression model, the closer it will be to zero, because it will be adapting to the training data. So that's why we should never judge a model, evaluating the model with the same data that was used to training, because it's always very optimistic. When we use the data, when we test the model, try to validate the model using the data that was used to train the model. Okay. And the true error rate, the test data is with the yellow. Okay. You can see what happens here with the order of polynomial used, and this is the k nearest neighbor. This is the k nearest neighbor. It's graphed by versus 1 over k. Okay, so this is k equals to 10. Okay, it's k equals to, sorry, 1 over k. Yeah, 1 over 10. Okay, but you can see in both cases that the degree, if we determine the degree of the polynomial with k-fold cross validation, we end up very close to the true value. Okay, now that I don't have the true value here, but I have, if I use in the test data, I would choose a k equals to 3, which is the k that we chose in the previous slide when we actually we drew the boundary, the base boundary. So k equals to 3, the polynomial of degree 3 was the right choice. And here the right choice would be k equals 2 with k tenfold cross validation would be with the test data, that'll be this one here, 0.1. So it'll be k equals to, no, I'm sorry, this is k equals to 1, right? K is equal to 10. With k equals to 10 in this case. For the 10 k nearest neighbor. Okay. So in general, generalized cross validation, k folds and repetitions. This is without repetitions. If we do it repetitions, that gives us a better estimate and less variance. Okay. Now let's talk about the next concept. Next concept is bootstrap. Bootstrap is another resampling method that can be used for the same purposes that we use cross-validation. Can be used for the same purposes. But it's also used, it's used to lower density estimation, for example. Because it can be used to quantify the uncertainty associated with statistical learning method. If, for example, in the regression model, if we do not have normality, one way that we can use to compute a confidence interval for the parameters of the regression model is to use bootstrap. That's a common method that's used when we do not have normal distribution in the errors for the norm in a regression, in a linear regression model. Okay. What it does, we take a sample with replacement from the training data. This is also with the training data. We take a sample with replacement containing the same number of observations that we have in the whole training set. Okay. In the whole training set, if we have 1,000 observations, we take a sample of those 1,000 observations that has 1,000 observations that will be replacement. The observations that are left out of those that we select are called out of bag. Those are the out of bag observations. Now, bootstrap error rates tend to be greater than those of k-fold cross-validation. But in the average, about 63% of the data are represented at least once. So that this technique has a bias that's similar to k-fold cross validation with k close to 2. So it has a small bias, and it's similar to a k-fold cross validation with 2 folds only, but it has the error rates tend to be to overestimate the actual error rate. This is how it works. This is the original data. So in the bootstrap sample number 1, we took this observation. In sample number 1, we have this one here. This one. And then we have this one also here. We have this one. And then we have this one 2 times, right? And we have this one 2 times because it's with replacement. Okay. And the ones that are left out of this set are these ones. So we model with these observations, we model with this, and we predict on these 3. Okay, that's a bootstrap procedure. We do sampling with replacement, take the bootstrap sample, and leave out, and the observations that are left out are the out-of-bag observations, and the model is tested on those out-of-bag observations. Is the concept clear for the bootstrap? This is the same data that we saw in slide 5. 10-fold cross-validation with 3 repetitions. This is with 3 repetitions to determine the value of k is in a k-nearest neighbor model. And you can see here for different values of k, we have values of accuracy and the kappa statistic. We'll look at the accuracy here. Remember that simulated data were almost balanced, so we can use the accuracy as a criteria. And as you can see with k equals 5, I have an accuracy of 70.6%, 7 is 73.88%, and the maximum is around here, right? The maximum is 75.86%, right? It's between these two. Okay, that's the maximum is between those two. So it will be between 9 and 11. We could choose 10, for example. Okay, they're too close. Doesn't matter. Now, this number here, each one of these numbers come from the average. If we did 10-fold cross validation and repeated that 5 times, no, how many times did I say? Repeated like 3 repetitions. So this is the average accuracy for 15 samples. I mean, no, 30 samples, okay? 30 models. So 30 models were fit, and the accuracy was computed for each of the 30 models, and this is the average of 30 models, the average accuracy for 30 models, okay? The best was k equals 11. It's very close between 9 and 11. I could choose 10. We'll talk later about a rule, that's the one standard rule, the standard deviation rule that says that if my criteria is accuracy, and I have 2 models that give me accuracies that are within 1 standard deviation, the second model and the second best model is within 1 standard deviation of the first model, but it's less complex, a simpler model, then I go with a simpler model. That's the one standard deviation rule. Now, some considerations, and we've mentioned some of these things, when we're splitting the data. First, a single set to use for testing has limited ability to characterize uncertainty. That's why we do repetitions in cross-validation, K-fold cross-validation, because then we have several testing sets to evaluate the model. Okay. That's better than having only the results of one in one test set. Now, proportionally large test sets divide the data in a way that increases bias in the performance estimates. The larger the test set, the larger the bias in the performance estimates. And we usually want to do, if the computer resources we have allow us to, we want to select a very large percentage for the trading, 75%, 80%, in some cases 90%. For example, in a project we did with a bank here to detect money laundering, we used 90% to train the data because we have 4 million transactions. So even though the set was very unbalanced, taking 10% of the 4 million transactions was enough to test it. Okay, so it depends on how many observations seem reasonable to test the model also. Now, with small data sets, we may require all possible observations to estimate the model. That's one thing that happens. With small data sets, if it's very small, it's probably better to use Bootstrap than use cross-validation, because we're selecting a sample with replacement, we're getting the same number of observations, really, every time we fit the model. Now, the uncertainty in the test set can be so large that different sets may produce very different results. Now, there are differences also in the robustness of the models to the training data that is used. And we evaluate that by the variability that we have in the estimates of the classification error or the area under the curve. Resampling methods can produce reasonable predictions of future model performance. Again, tenfold cross-validation is recommended if a sample size is not too large. And if it's too large, we could use a smaller set of folds, okay, folds for cross-validation, even fold cross-validation if it's too large. Because remember the training data, the larger it is, the more resources the algorithm needs to compute the model, to train the model.
Teacher.
This is something that we'll start looking at. This is comparing two models, okay? This is comparing, what models are here? KNN, K nearest neighbors, and logistic regression. If you look at these charts, if accuracy is the criteria to select the model, these box plots are very useful because they give us, remember, we used here 10 folds and 3 repetitions. So we have 30 data points that created this box plot and 30 data points that created this box plot for each value of the flexibility, for example. Now, so we'll have 30 times, if we use in the K nearest neighbor, we use 10 different values of K. That'll be 10 times 3 folds, no, 5 folds, 10 folds, was 10 folds, 3 repetitions, right? So 30 times 3, we fit the model essentially 300 times. So we have 300 data points that are represented in these box plots. So that gives us a very good idea of how robust the model is for different sets of training data. That variability. When we have in KNN, we have smaller variability for accuracy than in the kappa statistic. Okay. And the variability is almost the same in K nearest neighbor as in logistic regression. And the maximum, see the accuracy, the maximum is here and here, right? So the maximum accuracy that I achieved is very similar. However, the mediums are also very close. The smallest value for the accuracy that I obtained with KN and N is larger than the smallest one for the case of the logistic regression. If we were have to choose between these two models, then which one would you choose? And what are the advantages or disadvantages of choosing one versus the other? See, the maximums, the distribution looks very similar for the measurement of accuracy. So if I were to choose among these two models, there's no huge differences. I'll probably choose logistic regression because it's interpretable, right? I can interpret the coefficients of regression model, and I cannot interpret the KNN algorithm. In logistic regression model, we know which variables are the more important to predict whatever we're predicting, and whereas in KNN, we don't know that. The other disadvantage, in KNN, we need the whole training data set to predict. In logistic regression, no, we just have the model with the coefficients, that's it, okay? If I had a different situation, for example, if instead of having this chart like this, I had it like this, see, if this was a choice, and this is, let's suppose I'm going to make up here, this is neural networks. Then I would choose this one because that has higher values for the accuracy and has smaller variance. It's more robust to different training samples. So this type of chart will be very useful when we evaluate and compare different models, because that will help us determine which is the best model to use in a given situation, okay? And this is what we just mentioned, okay? So we'll go over the script next time. If you can